The next question on this chapter of mathematical introduction based on this section on linear vector spaces is the following. So this is exercise 1.1.2. This question says that consider the set of all entities of the form A, B, C. So it's a triplet. So we have three numbers A, B, C in this format, where the entries meaning the A, B and C are real numbers. Okay. Now for this set of entities, the addition and the scalar multiplication. Remember that for linear vector spaces, we have defined the addition of the vectors and scalar multiplication. That was the definition based on which we had certain axioms, and scalar multiplication are defined as follows. What is the definition over here? It says that if we take two such entities A, B, C and D, E, F, then their sum is given by this entity. Okay, so this is the addition. Now for the scalar multiplication, we take a scalar and multiply by this entity. So what do we get? We get fine. And all these numbers A, B, C, D, E, F, everything, all of these are real numbers, that is defined in the given question. So what is the question now? The question says, write down the null vector and inverse. So we want to find out the null vector and inverse for a given entity or vector A, B, C, this for triplet in the given vector space. Then show that vectors of the form A, B, 1. So the third entry over here is fixed at 1. Do not form a vector space. Do not form a vector space. So this is the question that we have to solve. So let us just read the question again. So what this question says, it says that we have the entities of this form. This is a triplet A, B, C, and all these entries in this entity are real numbers. Now we have defined the vector addition and scalar multiplication. We need these two definitions for the linear vector space, and then we want to find out the null vector and inverse over here for each entity. Then the next task is to see that these kind of format of entities where we fix the third entity to a value of 1. So these kind of entities are not forming a vector space. So when we say that they do not form a vector space, it means that the axioms are not satisfied. So we saw 8 axioms in the previous video. So if any one of those 8 axioms are not satisfied, then that means that that particular set of entities do not form a linear vector space. Just to remind you, we will just look at what those 8 axioms were. So for a linear vector space, we need certain entities called vectors, and then we defined the vector sum for it, and then we define a scalar multiplication for it. So this is the scalar multiplication for it, and then we have these following 8 axioms. The first one is closure property, then there is distributive property for the vectors, so it is scalar multiplication is distributive in the vectors. Also scalar multiplication is distributive in the scalars as well. So we have these 2 distributive properties for scalar multiplication. The fourth one is the associativity of scalar multiplication. Then we have 2 axioms based on addition. Addition is commutative, addition is associative. Then finally we have one definition of null vector. So a linear vector space needs to have a null vector, following this sort of a rule that the addition of the null vector to a given vector leaves that vector unchanged. And then lastly we define an inverse of a vector. So adding a vector to its inverse would result in getting the null vector. So these are the 8 axioms. If even one of these axioms are not satisfied, then that means that the set of this collection of objects do not form a linear vector space. So now we can come back to our question. So when the question says that show that certain group of objects do not form a vector space, we mean to say that basically those axioms are not satisfied. So let us start solving this question step by step. So the first part of this question asks us to find the null vector. So null vector. Now clearly the null vector in this triplet format is 0, 0, 0. Now why so? We will see. So let us add this to a given vector. Let's say we take this vector, we add what we propose to be our null vector. Then what do we get? By this definition we get a plus 0, b plus 0 and c plus 0. So by addition of real numbers, we know that this is nothing but a, b, c. So what do we get? We get that if we take a vector and add this 0, 0, 0 to it, we get back the same vector itself. And from the property of uniqueness of a null vector, we know that there is only one null vector in a given linear vector space. So we have found out our null vector given by this 0, 0, 0 triplet. So this part is done. We have found the null vector. Then it says find out the inverse. Now inverse. So let us propose that this, let us say that we have a vector a, b, c, and then we propose the inverse for this vector to be minus a, minus b, minus c. Now how can we be sure that this is the inverse? Again, let us add the vector to its inverse and see what do we get. So now by the definition of addition defined here, what is this? This is a minus a, actually we should write it a plus minus a like this, then b plus minus b like this, lastly for c. So what do we get finally? A plus minus a is nothing but a minus a, that gives us nothing but 0. So it is 0, 0, 0. So what does this say? That the sum of two vectors over here, a, b, c and minus a, minus b, minus c, is giving us the null vector. So this plus so we are getting the null vector, and by the definition of inverse, we know that if we add the inverse of a vector to the vector itself, then we get the null vector. So, and also inverse is unique. We saw that in the last video, the property of uniqueness of inverse. That means minus a, minus b, minus c is the unique inverse of a, comma b, comma c. Why? Because adding minus a, minus b, minus c to a, b and c gives us the null vector. So we have also found out the inverse. The third part of the question. So we have entities of this form, and we need to show that this does not form a vector space. Now from this inverse, we can see that what will be the inverse of this? Inverse of this entry a, comma b, comma 1 would be what? Minus a, minus b and minus 1. But note that this last entry, minus 1, this is minus 1. But we wanted all the entities to be of the form a, comma b, comma 1, which means that the first two entries can be anything, but the last entry, the very last entry that we have, this one, this has to be 1. But for the inverse, what we are getting, that the last entity is coming out to be minus 1. So what does this mean? This means that the inverse minus a, minus b, minus 1 is not of the form of a, comma b, comma 1. So inverse does not belong to the set. Does not belong to the set of entities of this format. Why? Because the last entry is fixed to be 1, but for the inverse we get minus 1. So this minus a, minus b, minus 1 is not of the form in which the last entry is 1. That means these kind of entities do not have an inverse. And by the axioms of the linear vector space, we know that the inverse needs to exist. The existence of inverse is required for a group of objects to be called a linear vector space. So lack of inverse would mean that these entities do not form a vector space. A linear vector space, that is to say. So that means that if we do not have the inverse, then they are not forming a vector space. So we have shown this last part also, that a, comma b, comma 1 do not form a vector space.